Okay. Actually, if anybody wants any, I do have this, but. All right, good. That is not what I want to do. That is, okay. Awesome. Extra. Thanks. Okay. Great. Are we all set to start? Yes, we are. Good. So I'm on camera. So greetings. This is Math Econ, Econ 464. Yeah, that's a good start. Assignment. This will be due a week from today, but I may as well just give you these things well in advance. Would be those problems, and say just a little bit about them before we get going here. The first two are really, I think, well, the first two I think are really straightforward, pretty easy. Sometimes people run into a little bit of difficulty with 3.1. 3.3 is not straightforward. So with all of these, what you should do is just go do as much as you can with them, work on them, make as much progress as you can. If you don't get them perfectly, turn them in, do something. There was a saying when I was at NYU, which was actually, I think, quite true, that when you were working on it, you'd get exams and you go like, this problem that they've assigned us is almost like, what do we do with this? Do something. Always work, throw some kind of first order condition or something like that. Get to work on it. And it might not be wrong, but make as much, might not be wrong. It might not be right, but it might not be wrong. But give them something to work with when they're grading. Just don't say, well, I can't do it, and punt. So, at any rate, let's see. Oh, you guys are going to turn in your problem sets, I guess. And I will start getting these back to you also. But great, thanks. I'll come around the other end of. Thanks. Thanks. Oh, I've got them? Great. All right, thanks. All right, great. Let's put that there. Some of you look kind of COVID-y to me. COVIDular or whatever the name is. Plus, I'm a mess. All right, good. Do you want to, any questions about these problems? Do you want to work through one or not right now? No? Let me just say, some people find them, I think, relatively straightforward or maybe even easy. I do want to talk at some point about problem 2.3. I think it's really an interesting one because of the economics in it as well. Won't do it right now. But let me just say something about a few of these problems. And what I recommend, oftentimes the best way to proceed is you have something like the following. You got f of x minus lambda g of x is your Lagrangian. And so you take the derivatives and maybe it's, let's do it this way, xy, g of xy. So we've got two variables. And so you end up with your partials will be dl dx is equal, this is our first order conditions, of course, will be equal to that minus lambda g of x. And we'll set that equal to 0, and then we will do f dl dy fy minus lambda g of y. We'll set that one equal to 0. And of course, dl d lambda, which is equal to this thing. And that's, of course, c minus that thing. Right? I'm counting that. So I've got I end up with c minus g of x, y, whatever that constraint is. Set that one equal to 0. Oftentimes, what I typically do when I want to solve one of these things, almost always the easiest thing to do is solve that for lambda, solve that for lambda. Get those crazy lambda things out of there. And so you end up with f of x over fx over gx equals lambda, and you end up with fy over gy equals lambda. And guess what? That means that we have fx over gx equals fy over gy. Really easy now to just solve either for x or for y, plug it into the constraint, and then just solve the thing for the one that you didn't. Let's say we solve that for x is equal to some function now of, I'll just call it little f of y. And so then I take that x, plug it in right there, solve the whole thing, and I get y is equal to some function of known parameters. And then I take that and plug it back in over here, and I'm done, right? That's especially when you're working like with the Cobb-Douglas functions, stuff just pops out so nicely. The exponents, you just work with exponents, and they just go, everything just goes so nicely and goes away, right? Okay. So for anybody who was getting like chasing your tail, trying to get these things done, the other thing to remember is that an answer to these things will always be x will be ended up equal to some function of known parameters. So whatever your parameters are, alpha, beta, those are maybe exponents on the Cobb-Douglas function or something like that. It'll be price, P1, P2, whatever, income, whatever the relevant things are. But it's all parameters. There won't be a y in here, for example. That wouldn't be a solution. If I found that, then I'm not done. I have to get the y out of there. It's an unknown, right? It can only be in terms of known variables. So we'd end up with something like y equals g of, I don't know, alpha, beta, P1, P2, I. That's a solution. Okay? Good? Okay. Probably, when you think about it, that's very obvious, but when you're working on problems, sometimes it's forgotten or lost. All right. Great. Any questions? Anything from last time? Last time, when I left off, we were talking about utility functions. I had a few more things I wanted to say about that, just a little bit. And so remember that what we were talking about was the nature of preferences. And if preferences satisfy certain conditions, then a utility function, we can represent them with a utility function. So if the preference relation from which we can get that and then derive that and that, weak preference, strong preference, and indifference. So if that satisfies, what was it? It had to be complete. That means you could rank any baskets. Had to be reflexive, which means a thing is not worse than itself. and it had to be transitive, and one more thing was continuous. If it satisfies those things, then it is can be represented by a utility function. So, so if this preference relation for an individual, if the preferences are, or preference, let's see, satisfies four conditions. I won't write them down right now. We just said it, and they should be in your notes. But the four conditions, then they can be represented by a function, utility function, U, which maps X, all the set of baskets, into the real number line, into R, okay? Such that for all, if X is preferred to Y, then, I don't have to say for all, if and only if U of X is strictly greater than U of Y, right? So if it gives you more utility, it means it was preferred, is what the kind of in English that is. Okay, great. And so we're not going to work through a proof on that, but this holds for any monotonic transformation. And so what do we mean by that? Well, what we mean is this is not a unique, the utility function won't be unique. You can generate a utility function like that, but then you can do any monotonic transformation to it, like square it or add 10 to anything that preserves the order of baskets or the ordering of that ordering will also be represented. So here's a monotonic transformation of f of, here's what we mean by that, f of u of whatever is in there. That's our transform. And what that would mean is that those preferences are also represented by, you could also say f u of x would be greater than f u of y. So f is my transform that I plugged in here. Okay, that holds if and only if u of x greater than or equal to u of y. Okay, that would be the definition of a monotonic transform, basically. All right, great. So the implication of this is that the only relevant feature of the utility function is the ordinal character. That is, how does it represent the underlying preferences? Does it show that they give, if that's preferred to that, then that has to give a bigger number than that. That will also give a bigger number than that. Okay, great. Now, suppose, here's what I want to say about that, and just illustrate something here about the importance of that and indifference curves. Suppose that we have this represent some set of preferences for some person. Okay, that's my preferences over x1 and x2. And now we're going to have V is a monotonic transform of U. Okay, great. And so in that case, we know that V U of x is greater than V U of y, if and only if U of x is greater than U of y. Okay, great. Well, so what? Well, let's take a look at the indifference curves, at what the indifference curves that we're going to get for this. And the indifference curves for this one will be given by that total differential. And so we will have du dx1 dx1 plus du dx2 dx2, and that will be equal to 0. And again, that's the marginal utility of x1 times the amount of change of x1, marginal utility x2 times the amount of change of x2, and those are balanced so that there's no change. We're moving along the indifference curve, right? Right. Okay, great. And so as we already know, that means that the slope of the indifference curve is dx2 over dx1, which is equal to d du dx1 over du dx2. Oh, there's a minus on it. Okay, great. So we know that the slope of the indifference curve is the marginal rate of substitution. Yep, yep, we already knew that. But what about the indifference curves for this thing? If we go ahead and write the total differential for that, we end up with dv equals v prime, where that's the first derivative of that thing with respect to the function using the chain rule, and du dx1 plus v prime of u du dx2 equals 0. Great. Well, it's different. It's got these units in it. But go ahead and solve that to find out what the slope of the thing is, and we find out that if we go ahead and solve, we still end up with dx1, dx2, I'm going to do it that way, dx2, dx1 equals minus v prime u du dx1 over v prime of u du dx2, and those things, that's division by of a thing by itself. I forgot to get the minus here. And so that's obviously equal to du dx1 du dx2, put the minus on. Great. So they are the same. And when you find the solution to it, what's the solution at the optimum? Oh, well, let's see. That'll be equal to p minus, it's the slope of the budget constraint, p1 over p2, which is equal to minus p1 over p2. That's at optimum. Our optimum condition will be the same. It gives us the very same outcome, right? It's the very same set of preferences. Does that make sense? Yes? Okay. It's these, we don't even need a utility function to do economics, but it simplifies things because we can work with our calculus and such. All right, any questions? Again, this is probably mostly not very, any questions or any thoughts, objections, anything? No? Occasionally there are objections from some of the, mostly the followers of Rothbard, who will say, Murray Rothbard, the Austrian, who will say that, well, there's something all wrong with this. But in fact, this all, given those assumptions, which all make sense, possibly not continuity, but I don't know what hinges on it. This lets us use calculus and lets us draw this stuff as nice graphs, but I don't know any policy or economic result that hinges on continuity, really. True, I've assumed that I can tell the difference between that cup of coffee and one that has a microgram less of coffee or something in it, or 1 molecule less or something. And that's not, coffee's not infinitely divisible, I guess, because it breaks down into molecules or something. All right, is that it? I don't know anything that hinges on that. You can assume continuity for the most part. I actually can think of one example that I sometimes use in Austrian economics where it's useful to not think in terms of continuity to see a result, but it isn't essential. So anyway, so I do all this. Oh, isn't that cool? Anyone? So great, one person thought it was cool. So, when I was a kid, I saw the movie Von Ryan's Express, and there's a line, if only one escapes from the prison camp alive, it's a success. So I always figure if one enjoys it, that's all that matters, even if it's just me. Well, hang on a second, though. Am I being too easy on this stuff? What is marginal utility, anyway? Because we often talk about diminishing marginal utility. You go into an Econ 202 class, and they start lecturing you on the importance of diminishing marginal utility. And here I said, well, it's kind of arbitrary, right? Oh, it's really arbitrary. Here, look at what I've just said. I have just said that, okay, let's do a monotonic transform to a utility function, okay? Let's try this one. Yeah. I guess that color is good enough. No, stick with these ones. Here we go. Here's a nice utility function. U equals x to the 1/2, y to the 1/2. Nice Cobb-Douglas utility function. Oh, this is great. Because we know that the marginal utility here, let's try the marginal utility for equal to du dx1, which is equal to 1/2, just do it this way, y over x to the 1/2, right? And, oh, cool, that's greater than 0. Well, marginal utility is positive. We'd like that property, yeah? Okay, and what else can we say? Well, let's take the derivative again of, in fact, it's easier to not do it that way, so we can really see what's going on. There's x to the -1/2, y to the 1/2. And we see that that's necessarily positive as long as we're consuming positive amounts of the goods. Yeah? And then secondly, let's look at the next derivative. And that's going to be equal to, let's see, -1/4 x to the -3/2 y to the 1/2. Oh, it's negative. Cool. Diminishing marginal utility. Just what I wanted, right? Except I've just gotten through explaining to you that this holds. Let's do a monotonic transformation on that. And in fact, let's square it, and then let's square it again. Okay. Just erase that. So that should be equivalent to, what do we have here? V equals x1 squared, I guess we're doing y, y1 squared, right? It's not y, x. x1 squared, x2 squared, right? Monotonic transformation. I squared both sides twice, right? Or took it to the 4th. Okay, good. So what do I end up with for my, oh my goodness. It looks like dv dx2 x1, do it that one, is equal to 2 x1 x2 squared greater than 0, just like I wanted. But then I get this one is equal to increasing marginal utility. This is what I did that caused Kadim Noré to suddenly just goes, I thought he was going to start crying when he said, I've just lost my faith. I'm going to go back to physics.
Wouldn't it be, like, should you incorporate
What negative?
So like your x to the 1/2, y 1/2.
All I do is, let's see, if I go u squared is equal to xy, right?
Yeah, but I mean the solutions.
And so u squared squared is equal to x squared y squared, right? Right. So I think when I take that and call that v, I get that. I take the derivative of that, I get that, and then I take the derivative of it again, and I get that, right? Yes? Let's see. I think so. Yeah, right? Okay, well, here's the thing, is that what are we talking about here? And so if you pick up Mark Blaug has his History of Economic Thought book, Economic Theory in Retrospect, there's a line somewhere way in it that says that modern economics dispenses with diminishing marginal utility. What's he talking about? This is what he's talking about. When we take this approach, geez, I hope you don't all drop economics now and go back to physics. But no, don't do that. You won't do that. Here, let's get this stuff out of here. Let me show you what is actually going on and what we mean by all this. And maybe restore some of your faith in reality. Let's go ahead and graph something here. Let's say that that's, in that dimension we have x1, in that dimension we have x2, and in that dimension we have utility. So in other words, I'm drawing a 3D graph, right? So it's like, right? That's the sound of those things going. You just have to have enough dimensions, but you realize that happens in the sound dimension. Anyway, so this is what we're used to thinking of. Okay, there's our, that would be a level of utility, that's a level of utility, that's a level of utility, and that is, right? Okay, and what is happening, so we just give them U0, U1, whatever. And so those are the around the back side, if you can't see through the utility mountain. So there's what we typically think of. Great. And that would show that this person has diminishing marginal utility, although that's not what that partial was. That showed that it was actually getting smaller as we increase this way. Okay. But here, what we're saying is that the indifference curves are the projection of those level curves down into this this x1, x2 plane, right? It's a topographic map of utility, right? Okay, that's what we have. And so what we're saying is that that is equivalent to, there's x1, there's x2, and now instead we're doing the transform. There's v. It could be something like that. And so here's our slope, our things. Right? And we project those. All we care about is the topographic map, the level curves and the relationship among them. We don't, the distance apart doesn't matter. It doesn't matter if it's increasing that way, increasing that way, decreasing that way, or even, you could do constant. Doesn't matter, right? Okay, that's the first thing. And the other thing is that going this way, this one could actually be marginal utility increasing, but it has to be decreasing with respect to the other good, relative to it. That's all that matters. Okay? That's what we're getting at with this. That's why Mark Blaug can say something like, well, we dispensed with diminishing marginal utility. You know what that actually is? A very long-winded mathematical way of saying the utility function is ordinal. It's just an ordering. It's order. The number doesn't really mean anything. But Austrians, from the get-go, were saying the utility function, not utility function, is ordinal. Preferences are ordinal. Rankings are ordinal. And that means that the distance between them doesn't make any, there is no meaningful distance between them. It's just an ordering, right? So most of you have heard this. If you've been through my History of Economic Thought class, we talked about that. This is the kind of significance of it. The things that I have shown here are actually compatible with the Austrian, without getting into the head, the Austrian concept of diminishing marginal utility, which in human action, Mises says, actually refers to the serviceability of an additional unit of a good, final good, equally serviceable. It refers rather to the purposes and the order that people satisfy them. Okay. Yes?
So how do people outside of the Austrian school, they agree with that same?
This thing that I just get.
Yeah, they agree with it.
What Mises said?
Yeah.
I don't think they pay a good deal of attention to it, except when they're lecturing to undergrads. Actually, probably a more serious answer to that is that concept, so far as I can tell, most of the people, I was just reading some stuff on this last night to refresh my memory. I don't see them addressing that issue. Most of the people who really dig into the microeconomics of preferences are busy laying out the various axioms or the various assumptions or conditions that our set of preferences would need to satisfy in order to get a utility function, and then they just talk about the properties of the utility function. That's it. They don't go beyond that. This is, without going too, well, may as well mention this. I was reading last night, because what I really was interested in was whether or not anyone challenges reflexivity as an assumption. And it turns out you can find people arguing about reflexivity and what it means, but it turns out that there are two different definitions of completeness that are used. And I'm not quite sure what to say about it, but it depends on how you define completeness as to whether this is implied in completeness or not. I actually have a couple of papers that I'm going to read to see if I can make more sense out of it. At some point, it's more for entertainment, I guess, or if you really get into modeling this stuff. I don't know of anything crucial that hinges on it, but if you use one definition of completeness, reflexivity is implied in it, and using another one, it's not implied. And it's weird to think that a thing wouldn't be at least as good as itself, or that a thing would be worse than itself in rankings. So I don't know what it would even mean. I was thinking it would mean that if this were worse than itself, then I could make profit by going like that. I got rid of something that was worse and got something, wait a minute, that was a loss. Wait, there's a gain. I mean, I don't know, it is meaningless.
That'd be like the difference between expected and realized utility. Like I have a cup of coffee and I think it's worth something, and so I buy it. No, I have it. It's not worth something.
No, I think not, because that has to do with expectation, which adds a whole nother dimension. I don't know if I will, but sometimes when we get to uncertainty, we'll treat expected utility. And the proof of the existence of an expected utility function from the assumptions is actually is a lot easier. So maybe we'll go through that and just show you what it's like, if there's interest in that. So, I don't know. Questions? All right. Great, so much for that. But the bottom line of this is ordinal ranking is what we've really shown with that. And all that really matters are what the first order conditions will give us in that, and whether they are minimum or maximum. All right, great. Let's get that one out of the way. So I've got a couple of different things that I wanted to cover here. But I think the first thing I want to do is I really want to kind of move into, wait. Is that what I want to do? No. Oh, there it is. What I want to do now is extend our model, and we're going to start working on chapter 3. And I'll come back maybe and talk a little bit about a few more items in chapter 2, maybe. But chapter 3, in a sense, is kind of the core chapter. And this is where we're going to lay out the full approach to this. And so we're going to see, I'll put this over here. It doesn't really have to be part of the lecture. We're going to do multiple variables and constraints. And non-negativity constraints. And inequality constraints. And then finally, once we've done all that, we will have the Kuhn-Tucker theorem. And once we have that, we'll be really ready to do a lot with this class. This is right now is maybe the most, I wouldn't say tedious, but it might be the most tedious part. But let's start out and talk about, first of all, multiple variables. And so with multiple variables, this is pretty simple. We have n choice variables, and that will simply be, we'll put them into a vector x1, x2, dot, 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 all the way up to xn, and n is as big as we wish. So the vector x has n elements. And so we'll just call that a vector x, which is going to be has n components to it, n elements. Great. And very simple to extend the Lagrange approach. Our Lagrangian will now be L of x, where that's a vector, and then we'll put our lambda for our Lagrange multiplier. And so then we have properly defining we'll have a function that will handle that, and a scalar function minus lambda g of x. I should put the whole thing in. We're going to do lambda c minus g of x. Great. So there's a constraint. That's the budget constraint or whatever it is. That's the vector of goods that we could be purchasing. But now it's a whole lot of stuff. There's more than 2 goods in Kroger. So we go over there and we have a budget and we have to solve this thing. Great. And the first order conditions will be simple. First order conditions will simply be that we end up with Lj. So we're going to let J index these things. That's what Dixit does. Let's write it this way. X bar. So the optimal choice of those things and the lambda, chosen optimally as well, will simply be equal to 0. We'll settle. And how many of those are there? For all j equals 1 dot 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 to n. So there are a whole bunch of those things, right? One derivative for each one of those. x1, x2, x3, x4, all the way to n. And then L lambda, also of this. We'll also set that one equal to 0. And so we have a total of how many first order conditions? Someone just say it. N plus 1. N plus 1 first order conditions. And how many unknowns? N plus 1 unknowns. And so if the whole thing turns out to be solvable, which probably will be, with our problems at least, should be straightforward to solve. Okay, yes?
Is this a single variable lambda? So it's a single constraint?
Yeah, right now it's a single constraint. We'll look at the multiple constraint case next. Okay, I'm going to say what I've just told you seems very obvious to me, and I think it's obvious to you. Simply tell you, I can't tell you how many times, don't want to even think of it, I've had students on exams somehow forget that there's more than one first order condition when they start doing this. It's like, well, geez, that doesn't make any sense. There's a whole bunch of them, right? There's one for every, you have to take the derivative with respect, first of all, to x1, then x2, then x3, x4. That just symbolizes, that's just a way of writing that there's n of them without me having, if n is 5 million, I don't want to write down 5 million first order conditions right now on the board. Okay, so I can do that and I just did it that way, that's all. And it's obvious to you guys right now. Just make sure it's obvious when you do it on the exam. Okay, good, awesome. All right, good, questions? Well, all right, Conrad, since you insist, multiple constraints. And the case of multiple constraints is kind of interesting. And again, it'll be straightforward. But think about first of all, what we're talking about here. And there's x2. Let's just think that we've got 2 choice variables right now. But we might have 3 constraints. I'm going to draw 3 in. There's 1. I'm going to call that one G1. Okay, that's just the name of that one. And we'll call this one, we'll call that one G2. And then very cleverly, we'll call this one G3. And let's say this is a maximization problem. Okay, so what's the feasible space here? What do those constraints tell us? Well, we have to stay inside of G1, have to stay there, have to stay inside of G2 in there, have to stay inside of G3 in there, which means that right there is the feasible space. Okay, well, I don't know, what do we do now? Again, this is a very straightforward extension. We have n choice variables. And then we'll have m constraints. And a typical constraint will be gi. So Dixit indexes them with I. And then we've got the vector x in there, and that's simply going to be equal to ci. We're going to have to worry about that right there. That equality. And so we're going to have to get rid of equality before we're done with these things. What if it has to be equal to all 3 of these constraints in this problem? There's no solution. It can't. So equality, some constraints will not be binding, we suddenly think, if we're going to be able to treat a case like that thing, right? There's no place where all 3 constraints are exactly satisfied. Right? Right. Okay. Oh, okay. So we're going to have to, that's why we have the Kuhn-Tucker theorem. It'll save us. It is so, I don't want to be too much of a nerd, but it is so cool when we get it up. But let's go ahead. And what we're going to do now is define multipliers. And so we're going to have multipliers for each constraint. Lambda I for all gi of x. Define those things. And so we're going to have a vector of Lagrange multipliers, which will look like this. Lambda 1 dot 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 lambda m. And so for this one, you'd have lambda 1, lambda 2, lambda 3 would apply to those, right? Right, okay, simple. And so straightforward extension. And now we can write this whole thing down in vector form, which I will do. Get that out of here. And, oh, in fact, I've already done it. That's it right there, but now we have to think that that is a vector there, and that's an appropriate vector, that's a matrix there of all the components, right? So F and G are appropriate vector and matrix functions, and C and lambda are those things. Our first order conditions are going to be really straightforward. We're going to have the same thing as always. It's going to be dl dxj. We'll set that equal to 0. For all j equal 1 dot 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 m, and then dl d lambda I, set that equal to 0 for all I equal 1 dot 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 to m. That one's supposed to be n, right? Okay, m plus n equations and m plus n unknowns. Yep. Okay, good. Let's go ahead and tackle a problem with this and just see what we can do with it, okay? Any questions before I erase this? I think it's all straightforward. If you guys can solve the stuff we've already done, you can solve this. Or if you can set up the Lagrangian, this is really simple. So let's look at this problem. I want to do the following. Choose x and y to maximize. U equals x to the 1/2, y to the 1/2. Okay? Now I need a couple of constraints to make this more interesting, and so we're going to say it's going to be subject to the constraints 2x plus y less than or equal to 10. I got to put those in because some constraints might not be binding. We can already see that that's always a possibility. And what's the other one I've got here? I'm going to call that one constraint 1, C1. And the other one is 2x plus 3y less than or equal to 18. We'll call that one C2. Okay, great. And so let's go ahead and draw that thing so we can see what's going on. And we have y, x, and it should be something like 10, and I'm just going to wing it here on this, but that's 5. So that's what C1, that's what graphing that one should give us. And the other one gives us about, I guess about there, 6 and 9. Okay, and there's C2, okay? Great, and so there's our feasible space here. So we have to stay inside that boundary, okay? If each constraint in this case holds with equality, we already know what the solution is. If they have to hold with equality, we could actually solve it. It's the point where they intersect, and there's nothing more to do. If you just say, well, if I had written this problem down, great, there's nothing more to say. Forget that, just solve that thing. Okay, but that's not the problem I've written down. So we have, they could be less than or equal. So that means it could be anywhere along there. Somebody tell me, what's the Lagrangian? Just tell me. You guys do this now. We want to set this up as a Lagrangian, so L is equal to x to the 1/2, y to the 1/2, plus lambda, what? Okay, a square bracket, right?
Well, I guess you do two, so
What?
then you just rewrite the constraints basically.
So maybe, I don't know, 10 minus 2x minus y? That one, yeah, right?
No, because it's an inequality, so I've got it.
Well, hang on. Let's just say that the answer is yes, because the answer actually is yes. So we'll worry about that when we do the first order conditions, okay? But right now we'll just do that, okay? Okay. What else?
Well, that in parentheses should actually be a vector that's like a column vector, so it should just have a function underneath it.
Okay, so I could write it out as in matrix form. I'm not going to do that. Let's just write this out really simply. How about this? I'm going to call that one 1. I could use a different. I was just going to see if nobody else was. So Conrad's pulling all the weight here, and then he makes a mistake, and everybody else sits there. So he gets 5 points. Everybody else gets 0 out of 10. So never mind. Plus, let's try this. Lambda 2, we've got a second one in there, right? So I've just done my matrix or my vector multiplication here. That's all. And so that would be, the second one would be 18 minus 2x minus 3y. Great. So now I've incorporated, I got my objective function, I got my first constraint, and I got my second constraint in there. That's the Lagrangian. Okay. I'm going to, just for a second, show you. This is what it all looks like when you got a big thing. But we'll come back and look at that here in a second and see how it all fits. Let's do some first order conditions, first of all, for this simple problem, because this is an easy one. And typically, we'll do easy ones. So what would be the first order condition? Let's take the derivative with respect to x. Okay? Yes? Yes. And I'm just drawing it that way with the little subscript on there. And that will be equal to 1/2 x to the minus 1/2 y to the 1/2. And then must be what? Minus 2 lambda 1. Right? Anything else? Oh, wait, over here, yeah. Multiply that, I get minus 2 lambda 2. Huh. Okay? And I'm going to set that one equal to 0. What else? Ly equals, I think that's 1/2 x to the 1/2 y to the minus 1/2 minus, let's see, lambda 1 minus lambda 1, and then lambda 2 minus 3 lambda 2, and I'll set that one equal to 0. Okay? What next? Okay, how about L lambda 1, and that's going to be, pop that one out, 10 minus 2x minus y. I remember I said it doesn't have to hold with equality, so we'll put the inequality in. Greater than or equal to 0, right? Right. Yes? It might be that it doesn't hold with equality. So I'm going to put the inequality there, and then L lambda 2, and that would give me that one. 18 minus 2x minus 3y. Uh-oh. Now what do I do? Okay. The solution to this thing is very easy, actually, as it turns out. That's why I did this one. But before I start doing math to solve it, start thinking about what you have here. So first of all, are you going to ask this question? Will you get a corner solution with this problem? A corner solution, of course, would mean you were all x or all y. Will that happen? Why not? Nate. If you have a corner solution, what happens? What's the value of your utility function? 0. Can you find any number at all? If you have even an infinitesimal amount of each one, then you're positive, right? So you're not gonna, this won't give you if you're trying to maximize that, it will not give you a corner solution. You know you're gonna consume both goods, right? Okay, this is econ, so go ahead and cheat. Well, it's not cheating, but you look at that and you say, I already know that we're not having a corner solution, and so we rule that out, okay? When you're on an exam, when you're in your PhD program or wherever you are, like this class, you can take those kinds of cuts. You just write down, like, given that utility function, given that objective function, no corner solutions, I've already ruled out some possibilities. We know that it won't be there, and we know it won't be there. Where else do we know it won't be? Well, marginal utility is always positive for both goods, right? With that. I just showed that a little bit earlier with the Cobb-Douglas. Marginal utility is positive, which means you're always willing to consume more. The constraint, at least one constraint, must be binding, so we're not going to have a satiation point with that. We're not going to find a point like that, oh, that's optimal. So we know already that these things are binding, right? You're going to consume some of both, and that's why I felt secure in putting those down as 0 here. I might not always. What if that was the point or that was the point? It wouldn't necessarily be equal to 0. But since I'm consuming both, consume them until the marginal benefit and marginal cost are equal. That's the idea, okay? So that was safe. So I know that I'm along the boundary here, and I'm not there, and I'm not there, somewhere else, okay? I just made the problem a lot easier to solve, okay? I ruled out a lot of stuff. So what else can we say? One thing you could do is just start comparing points. You can also rule out, for example, it's not gonna, the optimum won't occur through there because you can't get there. And it won't occur along there because you can't get there. So what you could do, for example, is solve, you could plug in that point, figure out where those two things cross, plug in that point, and find out what the utility function gives you. And then you could solve the thing with one constraint and see if along there is better than right there, then that's your optimum. Or solve it with that one, and if what you get is along there, then along there is your optimum, because it's better than that. It becomes very simple just by, you don't even have to know the Kuhn-Tucker theorem to do that, right? Conrad. Good.
Can you just solve the system inequalities by subtracting the second, fourth first order condition from the third order condition? And then you get, because that eliminates the x, so then you'd be able to say that y is for sure greater than or equal to 8, right, negative 8? I guess that helps.
Well, I'm puzzled. I'm not sure what you're saying, but I think the answer to your question is no. But see if you can work it out and then show me what you mean. So what I've just told you a couple of tricks, more or less tricks, to solve this thing. When you're in combat conditions, on exams or problems or something like that. But you can already start reasoning. Marginal utility is going to be positive, so for both goods. So you'll always be the constraints. At least one constraint is binding. You just made the problem so much easier because you know it's not this. In general, you might not be able to do that. Anyway, I just wanted to. I wrote this ahead of time because it takes 15 minutes of class time if I write it. But this is just so you can visualize what we're talking about with all this. I've written it down here just in matrix form. That is to say, well, this is the whole thing in matrix form. but this would be a matrix, this is a scalar function of the vector, the n vector, and this is that's I erased it. That's the vector of all the lambdas, lambda 1 through m. And then this is the vector of the c's, c1 through m, and that's all those constraints, right? With all of the x's in it. And then I expanded it here just so you can see that. You can see it's conformable and everything works fine here. So that's what it would look like, and I didn't do much more with that. There's our first order conditions. That's what that means, that's what that means. But then what does this actually represent? It represents this whole bunch of first order conditions of, that would be that's L1, L2, L sub 3, all the way to L sub n. And so there's how they would look laid out, okay? Yes?
Is there a reason that you can set that equal to 0 when we have inequalities in that?
Now we're going to start working with inequalities on that one too.
Right, because if there's a mix, would you have?
Yeah, here's what it's going to be. Once we get to Kuhn-Tucker and see how that works, we will have this. I wrote it that way just now, but there's what it's actually going to be. And then that one will be that L lambda. That's just the string of all. I said it's obvious. It's just this, you just write down all of those constraints, and they will all be, depends on what kind of a constraint it is, but typically those will be greater than or equal to 0, right? Okay, good. All right, good. So I'll leave that there for a second. You can take pictures of it or whatever. These videos, incidentally, I'm going to make available to you guys. I keep meaning to send you the link, but I haven't done that yet, but I will. Somebody reminds me. Okay, great. Well, in fact, so this matrix has to be, this thing has to be non-singular if we take don't pre-multiply by the lambdas. But that has to be a non-singular matrix, but if it is, then it will be solvable. Okay, that's the constraint. And Lagrange's theorem holds for this multiple variable case, the theorem we already talked about. So now we want to talk about the non-negativity constraints on the choice variables. And that's the one thing that makes this a little bit, that's the next thing. That's the thing that Nate just raised. And so I'm going to have that. We'll see if I can get all this done in this session. Okay. We'll come back and we'll solve this in a bit. Or maybe I'll just have you do it. In fact, I just told you how to solve it. Turn that one in next period. How about that? Some people are looking at you like, I didn't write it down in the notes. Oh, well, you're good. Now, maybe I'll send it out, but if you actually don't have it, but might be, see if you can solve it. So let's do the non-negativity constraints. We require, so non-negativity for choice variables. And I already know that this blue marker is not showing up on the screen. So non-negativity for choice variables. And so here's our requirement. We're going to require that xj be greater than or equal to 0 for all j. But it could be 0. Okay, you can't consume, since we're usually thinking of how much capital we'll use, how much labor, how many atlatls we'll consume, whatever. You can't consume negative numbers or use negative numbers, but you might have 0. So we have to include 0 as a possibility here. And so our original optimality condition gave us the following. If you remember what we had written back on maybe the second day, we had something like this. Marginal utility for good I minus lambda pi will be equal to 0 if xi is greater than 0. If we're consuming some, then we'll consume until the marginal utility and the marginal cost are equal. Okay. Or less than or equal to 0 if xi equals 0. It wasn't even worth consuming because the marginal utility wasn't as great as the marginal cost. It might have been positive, but not as good as the cost of it, right? Right. Okay. Good. We did that before, and everyone seemed to agree with it. Well, those are our Lagrangian first order conditions. That is the Lagrangian first order condition in the two variable one constraint case for xi. So let's see a generalization of this. The generalization of this thing is for xj, j equals 1 dot 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 to m, we have that partial equals fj of x minus the sum of the, from I equals 1 to m of the lambda I that's the partial of the ith constraint with respect to variable j, and that will be less than or equal to 0. Okay, less than or equal to 0 is what we had there, and so that's what we have here, right? Okay, I think that notation is clear. I slapped it up on the board really fast, but that is Gij is the partial derivative of the ith constraint with respect to the jth choice variable. Okay, that's what our notation is saying there. Great. Well, we also know, though, that that means that xi must be greater than or equal to 0. Okay. And either that one is equal to 0 or that one is equal to 0. One of those inequalities has to hold with equality, right? Cool. And in other words, xj times lj x bar equals 0. If one of those has to hold with equality, then that condition guarantees one of them is 0, right? Right. Okay. Wow. Cool. Awesome. This is actually has a name for it. It's called complementary slackness. Complementary slackness, and that's with an E, not an I right there. Complementary slackness means that if one of those conditions hold with equality, the other one can be slack. That is, it's an inequality, right? That's what that means. So one of them has to be equal to 0, and the other one, we don't care. Okay? It's slack. It's not. It doesn't bind. It's not holding. Okay? Great. That's awesome because that's our first order condition right there. The first order condition in the multiple variable case, when there's a possibility that we don't consume every good, is simply that Lx, that's the whole vector of x bar, less than or equal to 0, x bar greater than or equal to 0, and complementary slackness xj bar Lx there, Lj. Okay, great. Yeah. Yes? Okay. So that should, wow. we can rewrite the whole Lagrange theorem to handle that. And we have, what, 5 minutes left? Wanted to say a little bit then about how to tackle the inequality constraints, like the constraints that are on our problem. And ideally, I think our time constraint might be binding here, but we'll see what happens. I'll just talk real fast. Now we'll do this. Let's look now at the inequality constraints. Okay. So now we're talking about how we're going to deal with those things, because those things could be inequalities as well. And so that's what we're going to talk about really fast. And so what happens if constraint isn't binding? How do we deal with that? Because I had those inequalities and Conrad wanted to add them or subtract them or something. But here's what we're going to do with these. And this means once we do this, we could have none of the constraints even be binding. We'll have a way of still solving all this stuff. This is why I think this stuff is cool. But one constraint might not be binding. So we're trying to do something like the following. We're going to, again, maximize, I'll just do it really quickly, f of x subject to g of x has to be less than or equal to c, might not be binding. And so previously, when we talked about this possibility, we had, and we did talk about it, p1 x1 plus p2 x2. If you remember in that second lecture, we considered the possibility that that would hold. And what did we do? What did we do? We said the following. We said, well, we'll just define a new variable, x3, which is excess income, or whatever that constraint is. And marginal utility of it will be equal to 0. And necessarily, if that holds, if x3 is greater than 0, that also meant that our marginal utility of income, our lambda, was equal to 0, right? I didn't want any more. We didn't care about it. We're going to generalize that right now. And so here's our optimality condition. Let me just cut to the chase. Marginal utility I minus, that's not where I want to cut to this chase. To really lay this out and show you takes more than 2 minutes. But guess what? I'm going to just show you what the final outcome is, and then take a look at the book. But I think it will maybe be clear, is that what you want to have is, we know now that our first order conditions are that f of x, fx, x bar, minus lambda g x of, like this, that one will be less than or equal to 0, and x greater than or equal to 0, and complementary slackness. And there's going to be a similar condition put on the constraints. And so that's going to end up being, you can see it this way, c minus g of x minus will be greater than or equal to 0. Okay. All of the lambdas will be greater than or equal to 0, and complementary slackness, that is lambda okay. So either a constraint will be binding, in which case that can be positive. That is, the marginal value of relaxing that constraint is positive. And the complementary slackness condition guarantees one will hold. Or else, the constraint is not binding. We got plenty of stuff, in fact, more than we need. And in that case, that one's 0. And that is the marginal value of relaxing the constraint. Doesn't matter. It's 0. And so that complementary slackness guarantees that. Okay, does that make sense? Okay, we'll do that again because it was rushed at the end, and we need to go through that. This is key. If you get the Kuhn-Tucker theorem, which is we've basically just done, then this is kind of the essence of the main parts of this discussion. So we will lay that out a little bit. So read chapter 3. You can start looking at those problems. Maybe see what you can do with that problem I had on the board. And I guess we're done. Okay.